welcome to Virtual Science. In the previous class, we have already observed what happens of the particle in an infinite potential well. That means if there is an infinite potential barrier, then what happens of the particle. Now I am interested to find out what happens of the particle for an finite potential well, and for this case I am considering the simplest one, simplest potential form, like V of x equals to 0 for x less than 0. This is equals to V0 for 0 to a, and again 0 for x greater than a, where V0 is the constant depth or constant height of the potential barrier. Now a particle of mass m is coming to the barrier, and energy of the particle is E. So what happens? This is the case where, first case, we can say, where we can see that energy of the particle is indicated by red ball, energy is E, and energy of the particle is E greater than V0. That means case 1. From this pictorial, that this is the potential barrier at the potential barrier of height V0 starts from V0, sorry, V equals to, start from x equals to 0 to x equals to a. And the second case may arises that the energy of the particle E is less than V0. That means case 2 is energy of the particle is less than V0. So what happens for both cases? As we can see that from the first case, that as the energy is greater than potential barrier, we can consider easily that the particle can overcome the barrier. That means it can go from x less than 0 to x greater than a. But what happens for case 2? That means energy E less than V0. Classically, this is not possible for this particle to overcome this barrier, because energy is less than potential barrier, and from your experience you can obviously say that this is not possible. This two region particle cannot move beyond x equals to a. But in quantum mechanics this is possible, because in classical physics particle is treated as particle. This is particle, but in, and particle must have energy greater than the barrier to overcome the barrier. But in quantum mechanics, as the particle is behaved as, is considered as wave, so wave can propagate also, though the energy is less than the potential barrier. That means quantum mechanically it is possible for case 2 to transmit or to propagate through the potential barrier, though the potential barrier is greater than the energy. That means we can get a finite value of transmittance probability of this particle in the region 2 for quantum mechanics. Now what is reflection probability and what is transmittance probability? Reflection probability means how much wave or particle reflected in respect to incident wave, and transmitted probability indicates that how much wave or particle propagates or transmits through a channel, through a barrier, or like this with respect to the incident wave. So now we are interested to solve this problem. So first of all, we will do this case for case 1, that means E greater than V0. Okay, then we will come to our next case, E less than V0. So first of all, I am now forget about the case 2, only case 1. So how to solve the problem? First, write down the Schrodinger equation. Have to solve it. For the solution, to get the wave function and have to put the boundary condition. Then we have done. So first of all, let us write the wave function, and for the wave function we have to write the Schrodinger equation. So I am writing region 1, region 2 and region 3 for the case 1. Region 1 indicates that potential is 0. That means Schrodinger equation in this case is equals to E psi 1, because potential is 0 in this case. This is for region 1. That means we can write down this equation as d2 psi dx square plus k1 square psi equals to 0, where k1 indicates square root of 2me by h cut square. This is from region 1. And from region 2, what we can get, that minus h cut square by 2m into psi dx2 plus v0 psi 2 equals to e psi 2. This will gives us d2 psi 2 dx square plus k2 square psi 2 equals to 0, where k2 is square root of 2m into e minus v0 or v0 by h cut square. Now why I am interested to write down e minus v0? Because we have considered the case for e greater than v0. That means e minus v0 is a positive term, and if v0 is greater than e, that means for second case we will write that v0 minus e instead of e minus v0. Okay, so this is for case 2. And in the region 3, what happens? Again we will write that in the region 3, this is similar to region 1. So this can be written as d psi 3 dx cube plus q1 square psi 3 equals to 0. This is for region 3. So I am writing the Schrodinger equations line by line for 3 regions. That means first region indicates that d2 psi 1 dx square plus q1 square psi 1 equals to 0. This is for 0 less than, sorry, x less than 0. For wave function 1. Second case, for x that is from 0 to a, and in the third case we can write down again this is for x greater than a, and k1 equals to square root of 2me by h cut square, and k2 equals to square root of 2m into e minus v0 by h cut square. Now we are interested to solve these equation I can say that equation 1, equation 2 and equation 3. These 3 equations can be solved by simple partial by ordinary differential equation, and the solutions are psi 1 x equals to a e to the power I k x, sorry, this is k1 psi 2 x equals to and psi 3x equals to, I am not writing e as constant because e is energy we have defined already. So these are the solution of corresponding on these corresponding 1 2 3 equations, and the solution can be obtained very much easily. So I am skipping this. Now a b c d and f g are the constants, and now I am interested which will be possible and which will not be possible. So from this equation we can say that psi 3x, the acceptable wave function psi 3x will be f e to the power I kx, because if you remember the potential, I am drawing this again, that this is x equals to a, and psi 3 indicates the region for x greater than a. For x greater than a, there is no barrier. There is no barrier. This is free, so there is no chance of reflection. So this wave propagate to the positive x direction. This is positive x direction. So the acceptable wave functions are this, because there is no existence of g to the power minus I kx, g to the power minus I k1x, no exist. So these are the acceptable wave functions for three region. We can say that psi 1 is for x less than a, sorry, x less than 0. Psi 2 is for x varies from 0 to a, and psi 3 for x greater than a. Now we have to use the boundary condition to correlate between a, b, c, d and f. So what are the boundary condition here? As we have already stated in the previous classes, that wave functions must be finite, single valued and continuous, and its first order derivative with respect to position, that means d psi dx, must also be finite, single valued and continuous. So we have three region 1, region 2 and region 3. So what we can see, that at x equals to 0, that means at this point there is a boundary between region 1 and region 2, and similarly there is a boundary in region 2 and region 3. This is x equals to a, this one, and here this one. So let's check. So for the boundary at x equals to 0, which relates between region 1 and region 2, what we can say, that psi 1 at x equals to 0 must be equal to psi 2 at x equals to 0, and its first order derivative must also be the same, that means d psi 1 dx at x equals to 0 equals to d psi 2 dx at x equals to 0. This is from boundary 1, that means x equals to 0, which relates between 1 and 2, and similarly we can write down from 2 and 3 from the boundary at x equals to a is psi 2 x equals to a equals to psi 3 at x equals to a, and d psi 2 dx at x equals to a equals to d psi 3 dx at x equals to a. So we have these, that means we have four boundary conditions, and we have to use these boundary conditions in the equation psi 1, in this equation psi 1 psi 2 psi 3, that means say that solution of Schrodinger equation to find out the constants. So let's do it. So from the boundary condition we can write that at the region at x equals to 0, that means relates between 1 and 2 region. Psi 1 at x equals to 0 equals to psi 2 at x equals to 0. This gives us a plus b equals to c plus d, and d psi dx is also continuous at x equals to 0. That means a minus b equals to c minus d. Here a term k1 will be coming out, here a term k2 will be coming out. That means a minus b will be k2 by k1 c minus d, because psi 1x a to the power I kx plus b e to the power minus I kx. So d psi 1 dx equals to I k a e to the power I kx minus b e to the power minus I kx, and d psi dx at x equals to 0 I k a minus b, because e to the power 0 equals to 1. Similarly, from psi 2 we can write down, and finally we can correlate between AB and CD. So this is our equation. Again I am writing equation 1, again I am writing equation 2. Okay, just for my case you can consider equation serial by serial. That means first one is for Schrodinger equation, second are the set of solutions, and third are the boundary conditions, fourth steps are the these conditions. So from this case we can correlate between A and B. Now now we have to apply the boundary condition at x equals to A. What we will get, that C plus D equals to f e to the power I k 1a e to the power I k 2a, because psi 2x equals to c e to the power I k 2 x plus d e to the power minus I k 2x, and I am now putting the value of psi 2a. So this will gives us c e to the power I k 2a plus d e to the power minus I k 2a. So what I have written is somehow wrong, and psi 3x equals to f e to the power I k 1x. So psi 3 at a equals to f e to the power I k 1a. So we can write c e to the power I k 2a plus d e to the power minus I k 2a equals to a to the power I k 1a, and the term from the fourth boundary condition, that means d psi dx, we can write down that k2 into c e to the power I k2a minus d e to the power minus I k2a equals to k1 f e to the power I k1a. So we have this one, this one, this one, and this one, these four conditions in our hand. So what we can write, that we have 5 constant and 4 equation. So we cannot find the absolute value of ABCD from here, but we can correlate between A and F, B and F, and we are interested to find all the term in F or A. So let's check. From these two equations, that means 3 and 4, what we can see, that c to the power I k2a to the power minus I k2a equals to f e to the power I k1a, and c to the power I k2a minus d e to the power minus I k2a equals to k1 by k2 f e to the power I k1a. Now adding these two equations, we can say that C equals to 1 plus k1 by k2 into f by 2 e to the power I k1 minus k2a, and d equals to, we can find the value of d from subtracting these two equations. This will gives us 1 minus k1 by k2 f by 2 e to the power I k1 plus k2 into a. So we can now define C and D in terms of f. Now we have to define a and b in terms of C and D. So adding these two equations 1 and 2, we can write down that a equals to 1 plus k2 by k1 into C by 2 plus 1 minus k2 by k1 into d by 2, and subtracting these two, we can write down that b equals to 1 minus k2 by k1 C by 2 plus 1 plus k2 by k1 d by 2. So I am writing down again the constants. That means a equals to 1 plus k2 by k1 C by 2 plus 1 minus k2 by k1 d by 2, b equals to 1 minus k2 by k1 . Sorry, 1 minus k1 by k2. Now arises the potential. This is the potential, and this is our incident wave. This can be a to the power I k1 x. This is our incident wave. This is our reflected wave. That is b to the power minus I k1 x. K1x, and this is the wave propagating through the positive x direction, and this is c to the power I k2x. This is d e to the power minus I k2x, and the transmitted wave is f e to the power I k1x again. So we are now interested to find the reflection probability and the transmittance probability. So reflection probability, how can we define this? This is reflection probability is the ratio of probability between the wave reflected to the wave. That means probability of reflected wave to the probability of incident wave. incident. Now, how to find the probability of incident wave? Now, the incident wave is defined by a e to the power I k1x, and for incident probability, this can be written as probability equals to minus I squared by 2m psi gradient psi star minus psi star gradient psi. This is for three-dimensional case, and for one-dimensional case, this can be written as minus I squared by 2m psi gradient psi del psi star del x minus psi star del psi del x. Now, our incident wave is I incident can be written as a to the power I k1x. Now, putting the value of there, I can find out the incident probability minus I squared by 2m psi a, and psi star indicates that a e to the power minus I k1x, as this is a complex number and complex conjugate of I is minus I. So this will gives us minus I k1 e to the power minus I k1 x, and e to the power minus I k1 x. Similarly, we can find the probability for reflected wave. That means reflected wave is b e to the power minus I k1 x. By the same method, we can find the probability of reflected wave. So the probability ratio R or RP, this can be written as ratio of probability reflected wave, that means which obtained from this, and incident wave from this, that means this will gives us fine. So what we can write, that ratio of ratio of probability of reflected wave to the probability of incident wave, that is the reflection probability is by this equation. And now if one put the value of b and a in terms of c and d, and if you put the value of f in terms of c and d, you will finally get the probability reflection probability ratio. Now what happens for transmission probability? In a similar way of the reflection probability, we can easily find the transmission probability. Transmission probability T can be written as probability of transmitted wave to the probability of incident wave. That means now transmitted wave is written as f e to the power I k1x, and incident wave is a e to the power I k1x. So in a similar fashion of the reflection probability, we can write down Tp equals to f square by a square. Now we can easily find this ratio because a can be written in terms of c and d, and c and a and d can also be replaced by f. So finally what we can get, that transmission probability Tp is 1 over 1 plus a minus b0 sine square a by a squared square root of 2m e minus v0. This is the transmission probability and this is the reflection probability, and this can be written as e minus v0 by v. So I am not going to prove this equation. Just put the value of AF for transmission probability, and for reflection probability put the value of B and A, and finally put the value of K2 and K1, where I am writing K1 again. K1 equals to square root of 2m by a squared square, and K2 equals to square root of 2m e minus v naught by a squared square. So these are the transmission probability and reflection probability. Just do the calculation for your sake and for your practice also, because these are important parameter, and you can check what happens for Tp plus Rp. What is the value of this? Well, I am saying that Tp plus Rp, that means the sum of reflection probability and the transmission probability is 1. That means Tp plus Rp equals to 1. So I request you to check all these equations. So check Tp and Rp also, and also check Tp and Tp plus Rp. Either this is 1 or not. This must be 1, but you should check yourself for your practice. So if you have any problem in this regarding these equations, please contact us. We will elaborate it in detail. Two case arises in this term. So this Tp is the transmission probability, Rp is the reflection probability. Now if E is very greater than V0, that means energy of the incident particle is much greater than potential barrier. Then what happens? Then the denominator term V naught square by E into E minus V0 will nearly equals to 0, because E is very higher than V0. Then transmission probability tends to 1 and reflection probability tends to 0. So if the particle has energy much higher than the potential barrier, then the particle will transmit freely without any reflection. And the case 2, transmission probability will be again 1 if sine square a by a squared, that means the term inside will be 0, then the transmission will be 1 again and reflection will be 0 again. So sine ax equals to 0 indicates a equals to n pi, because sine n pi equals to 0 where n is the integer. So we can write down the energy of the state that plus v naught. That means if a particle has an energy like this, then the transmission probability will be again 1 and reflection probability will be 0. That means the particle will transmit without any reflection if the particle has an energy like this. V0 is a positive. Now we can observe that The maxima of transmission probability is similar to the eigenvalue of one dimensional eigenvalue of energy of for one dimensional infinite potential barrier, because energy of infinite potential wall is n square pi square 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 by 2m square, where v0 is 0, and this effect was experimentally observed, and this effect is known as the Ramsauer Townsend effect. So if there is a particle of energy which is greater than potential barrier v0, v0 is positive, then we can find the transmission probability, reflection probability, and for different condition also. And now what happens if v0 equals to negative? That means v0 is negative, less than 0, then E minus v0 will be replaced by E plus v0 or E plus v0, whatever you can say. Otherwise all the calculations will be same. More will be discussed in the next class. Please subscribe our channel and comment in the comment box, and for further query please mail us at farsighteach@gmail.com. Thank you.